All right, so this is 7-4, similarity in right triangles. We did this progression for congruent. We did congruent polygons, congruent triangles, and then we had some special, we did the hypotenuse leg for the congruent right triangles. So we're following the same thing with similar shapes. We did similar polygons, similar triangles, and now here we are with similar right triangles. Okay, so there is this beautiful thing that happens with right triangles. When I have a right triangle like ABC here, and I put in an altitude, and I always remember altitude as it's the height of the triangle, so it goes from the vertex perpendicular to the base. When you put in an altitude, it creates two more 90-degree angles. Awesome. So, so they have the 90-degree angle in common with their parent, big old fatty ABC. And we know that they're similar because this big triangle has angle A, and this little triangle also has that same shared angle. So because I have the right angle and that shared angle A, these two triangles are similar by angle. And same with this little triangle here. When we rotate him around, he shares with his big daddy. He shares that he has a right angle just like the big guy, and he has angle B just like Big Daddy. So we can say that this little triangle is similar to the big one, this one, and this little triangle is similar to his big one, and then the two triangles are similar to each other because they share that 90-degree angle and angle C. Kind of. So these three triangles are all similar to each other, which is why we write down these similarity statements. Triangle ABC similar to triangle ACD. Triangle ABC is also similar to CBD, and ACD is similar to CBD. So that's a because of that special weird magic right triangle, that's all related. I want you to add, so let's put a box around these guys. And we're going to add a proportion statement to this as well. So we're going to put a little, although that's coming up next, but I want it all on one page so that you guys can use it as reference for later. Oh no, we won't. We'll do that. We'll be patient. We'll be patient. Okay. So it says, what similarity statement can you write relating the three triangles in the diagram? You guys are going to do this on your practice assignment, so it's super important that you be able to do it here as well. So we're going to take this triangle. I'm in fact going to make a copy of it. Nope, that's not what I want to do. Make a copy. And then, so my suggestion to you guys is that you redraw the triangle so that it matches the orientation of our original one here. So we're going to take this, we're going to flip it around, and when it's flipped around, we can see that P is the same as C. P and C. R is the same as A. S is the same as D. Nope, it's backwards. Hold on. It's backwards. There we go. There we go. Like that. Okay. So P and C, still true. D and S, still true. Q and A. And B and R. So once you know how your new triangle relates to the one we're using as reference, we can easily put these similarity statements together. So if I'm saying triangle ABC, well, it's no longer ABC. I did that backwards. So it's going to be triangle QRP is similar to ACD. A, which is Q, C, which is P, and D, which is S. Does that make sense? I'm using the triangle as like a little decoder. You can do that by looking at it as well. The big triangle, so you can say that this big triangle is congruent to the little guy. Then we do that again. Our big triangle, QRP, is similar to, up here, it was CBD. CBD, so that's PRS. PRS. And then the last one is ACD. So it's your original little guy over here. So ACD. QPS. Is similar to CBD. CBD, which is PRS. So when it's asking you to write a similarity statement, we have 3 triangles, so we need to write 3 similarity statements. Yes, Claire.
Is each triangle?
All right, so now we're going to talk about geometric means. Since we've been doing all this cross multiplying, there's a little side topic called geometric mean, and when we deal with similarity proportions, we're going to have to mess with geometric mean. So what a geometric mean does is it takes 2 numbers and sets them up into a proportion. So you're going to have 2 numbers, and it's going to set it up into a proportion where your first number over x is equal to this x over your second number. So if we were to put 4 into A and 18 in for B, so it'd be 4 over x equals x over 18. We cross multiply. We get 4 times 18. Sometimes it is not any easier to do the multiplication together. So I'm going to leave it as 4 times 18. And I'm actually, because the next step is we're taking the square root, I'm actually going to convert 18 into 2 times 9. So when you take the square root of both sides, you get the square root of 4 times 2 times 9 equals x. I made it into factors. You guys see how I split 18 up? I divvied it up into its factors because I want to find the perfect square that lives inside of 18, and that is 9. So the ones that are the perfect squares, I'm going to square root them and release them from their square root prison. So square root of 4 is 2, and the square root of 9 is 3. 4, 2 is not a perfect square, so he stays inside. And then I can calculate 2 times 3. For this section, we are going to write our answers in exact form. So there was no need for me to bust out my calculator here because I knew how to do this. I can do 2 times 3 without a calculator. So the geometric mean between 4 and 18 is 6 times the square root of 2. So this is us remembering that when we take the square root, we have to take the square root of x squared to solve for x. Any questions on this? Okay, so let's see how that applies here. So we had our similarity statements. We're going to get 2 theorems, 2 corollaries to theorems that are going to show that are going to make similarity statements and require us to do kind of a little geometric mean problem. I'm going to completely ignore this statement for a moment. I'm going to go back and I want you guys to do the same. You guys have room? Yeah, you guys have room up off to the side. So off to the side, go ahead and draw our original triangle. This is the Big Daddy. Remember, he's got a right angle at the top. A is on the left, C is at top, and B is over here. So we're just redrawing the triangle from the previous page. And then we drop in the altitude. He makes a 90-degree angle. And what was this letter here? B? Okay, so from our Big Daddy triangle being similar to these 2 little guys, we get 3 proportionality statements. We get AB over CD equals CD over DB. AB over AC equals AC over AD. And AB over CB equals CB over DB. Your job is going to be to look at your problem, match it up with your original triangle, and figure out which one of these 3 proportions you're going to use. You want to make sure you can fill in 2 of the items, because look, CB and CB, if I have CB, then it takes care of 2 out of the 4 sides in my proportionality statement. So let me show you how that works. I have this triangle here. I'm going to go ahead and flip it. And because I can do this better than I can draw it, we're going to go ahead and flip. I will rewrite these numbers so that you can see them a little bit better. So redraw this triangle. X is still on this side here. Y is the height of our big triangle. This is 4, and this is 5. What is the total distance of the base of this triangle? Sorry, I'll give you guys a second. Example 3, I just flipped it, so it'll make you feel better if I'll just show you here.
I was confused.
This side is X, this is 4, this is 5, our height is Y. There's one piece of information that we have that isn't blatantly written out. It's this distance here. What is the distance of the base of our big triangle? 9. So now we need to find the proportionality statement where we have 2 out of the 3 line segments. So this is A, this is C, and this is B, and this is D. So I have AD, I have DB, and I have AB. So I have AB, I have AD, I have DB, and I need to find, so let's use the first one. Let's use this one. So AD, we're going to use this one right here. So AD is 4, CD is Y, CD is Y, and DB is 5. So CD was the unknown value, so we're going to cross multiply and solve. So 4 times 5 is 20, and Y times Y is Y squared. Then we're going to take the square root of both sides. Square root of 20 is equal to Y. 20 is 4 times 5. The square root of 4 is 2, so I'm going to go ahead and release him. 5 stays inside, and I get Y is equal to 2 root 5. The next one I'm going to solve for, I need just a little bit more room. Sorry, robots. I need more room. Okay, so the next one I'm going to solve for is the X. X is on AC. We look here, there's no AC in this proportionality statement, can't use it. There is an AC, AC only appears here, so we got to use this proportionality statement. So here's where AB happens. So we're going to take this one. Okay, so AB is 9, AC is X, AC is X, and AD is 4. So we're going to cross multiply. 9 times 4 is 36, and that's equal to X squared. We're going to take the square root, and X is equal to 6. Okay, we're going to do that a second time. We're going to do that with this robotics problem. I would like to say I've never done this before, but that would be a lie. I have spent 3 years of my life coaching robotics. You know how in A Tale of Two Cities they say it was the best of times and it was the worst of times? The age of wisdom is the age of incredulity. It was definitely not the best of times. So in this situation, we're preparing for a robotics competition using this setup here. I am going to relabel so that it matches the one, so that it matches this one. Oh, where'd it go? What about? So I'm gonna relabel it so we get A, C, B, if you guys don't mind. Does anybody object to that? I want it to be A, C, B, just like our picture that we've been fussing with. Does anybody object? And then D is still D. So they give us some pieces of information that are already written on here. The distance from here to here is 20. AB, or this guy is perpendicular to the altitude. Point D. So they kind of give us all this information here. And we're supposed to find how far the robot travels from here to here. So we want to find this x value. So we're going to put a little proportionality statement together. We're going to look at our options. How could we write AB if we needed it? So the distance from here to here. So the distance of the base of our big triangle. How can we write that if we needed to use it? How did we write it up here? How did we write it up here? So this was 4 and 5. We wrote that as 9. This is x and 9. So how do we write that whole statement? 9 plus x. We're adding. We added them together. Okay? So when we don't have a distance, but we can put it together with an x statement, we put it together with an x statement. So technically we have AB, and we have CD, we have AD, and do we have DB? Okay, so I'm going to use this first one. So that means I'm going to go AD over CD. So that's the little base over the height. But we don't have the height, so I can't use that one, okay? Second one. AB is the total distance over AC, which is the left-hand distance. So AB over AC. So that is the total distance over this left-hand. Oh, I don't have that left-handed. Okay, can't use that one. Okay, so we're only left with AB over CB. AB is the total bottom. CB is the right-hand side. So total bottom over the right-hand side, I have that. So 9 plus x over CB equals CB, that right-hand side, over DB, which is the longer portion of the base. So CB over the longer portion of the base, which is x. Okay, so do you see how that process of elimination went? We couldn't use the first one because we didn't have enough information. We couldn't use the second one because we didn't have enough information. We're using the third one because we have enough information to fill in all of the sides. So now here it goes. Fun with quadratics. Yay! Quadratics! Oh my gosh. So we're going to multiply these together. So it's going to give us 9x plus x squared when we multiply those two together. And that's going to equal 400. When we did solving quadratics together last week, we wanted everything over onto one side of the equation. So I'm going to move 400 over here. I'm also going to take x squared and put him in the front boss position. So this is going to be x squared plus 9x minus 400 equals 0. Now, you can use quadratic equations. I'm going to factor this. Okay, x squared splits up into x and x. I need factors of negative 400. Our purpose is going to be they need to add up to 9 and multiply to give me negative 400. I'm going to start out with a couple that I know and we can eliminate. So we got 10 and 40. When I subtract those two, I get 30. So it's not 10 and 40. There are I know 25 goes in that because I can use quarters to make $4. So how many quarters will give us $4? 16 quarters will give us $4. So 25 times 16 is 400. When I subtract those two, do I get 9? Yeah, so the bigger one, so it has to be positive 25 and negative 16. So when you factor it out, you get x plus 25 and x minus 16. We're going to set each of those pieces equal to 0. This is the part of the problem where you forget that we were even working on a robotics question. So we're going to subtract 25 from both sides. We get x is equal to negative 25. We're going to add 16 to both sides, and you get x is equal to 16. Which one is the no-no one? We can't have the two answers. Negative 25 or 16, which one can we eliminate? Negative 25, you cannot go a negative distance. So the true answer is 16 inches. I know, but I did show every step.